All right, so returning to probability and statistics, a lot of this lesson is introducing, it's the first HL lesson in probability and statistics, and a lot of this is introducing a bunch of new terms that I am far too lazy to read, and you will not listen anyways. So instead of me doing that, let's just get straight to here and using some of these. So we have a student in Thailand who wants to determine the average amount of money that a Thai person spends each month on entertainment. He creates a questionnaire to help collect information and decides to use a systematic sampling method of asking every 10th person that walks out of a Starbucks at a mall near his home. All right, so keep in mind, a systematic sampling method is where we ask every, in this case, 10 people in some sort of location or locations. So with that said, there are some problems with this sampling method and how he's getting his data. And so the first part describes some possible problems with the chosen method. Well, this sample will be biased. It will overrepresent people from certain demographics and underrepresent others. In this case, it'll overrepresent people who happen to go to Starbucks, which is a particular demographic. It doesn't apply to the entire population of Thailand, as well as people who go near the mall near his home. Depending on where he lives and the mall near there, that alone will focus on most likely a very particular demographic of Thai people. And if we're trying to find information about the average Thai person, which we want to have some sort of sampling method that represents the population as best as possible. So this is a pretty bad technique to try to find data that is valid, that is unbiased. And so those are some of the problems with this. So what can we do to remedy this? Describe some steps to remove the bias. A few things we can do. First, ask people in more than one location. Nothing wrong inherently with asking at a Starbucks or a systematic method, but more than just that one location in that one mall. And try to find areas that relate to different demographics of the population. If you really are trying to find the average, relating to the average person in Thailand, you're probably going to need to find locations throughout the whole country, not just in one particular city. And if that's not doable, then we got to realize our data won't represent the average Thai person. It'll be only representing maybe people in the city of Bangkok or whatnot. And so those sort of steps, trying to greatly increase the number of locations and therefore the scope of the demographics of the different people they're asking, that's the key thing to do. Lastly, describe a reliability test that could be used to check the reliability of your data. So if data is reliable, that means if you repeat, or if other people repeat the survey or collect similar data, they should get similar results. If different people, or when you repeat or collect data from a different group, if you're getting data that's significantly different, then your data is not valid. At least some of the data is not valid. And so how can we check the reliability? I'm going to go back here. We can look at some of these reliability tests. A test-retest is where you distribute the exact same questionnaire or survey just at 2 different times. So one thing he could do, assuming he improves removes a lot of the bias from his study, is do this on more than one day. Go to these locations on more than one day, and then compare your data and see if you're getting similar results. Another option, what we call parallel forms, is where you create 2 different surveys, but they're designed to answer or to gather the same information, but they're worded or set up in a way that it's not exactly the same. Maybe the questions are slightly different, or but ideally for this, if we give the same people the same 2 surveys, we should get similar results, regardless of how the surveys were worded. And so giving 2 different versions of the same survey is what we call a parallel form. The test-retest, which just requires waiting and doing it again with a different group of people, requires using the same survey. Lots of approaches here. In this course, you're expected to be familiar with those 2. All right, I want to now talk about this expected counts condition. And earlier in the course, we looked at the chi-squared, some various chi-squared tests, including the test for independence or goodness of fit. I'm going to focus on tests for independence here. One thing we didn't mention before is that if we are going to use any chi-squared tests, our expected counts always must be at least 5. And so that's what I mentioned right here. The expected counts condition is that all the expected frequencies or the expected values must be at least 5, if not greater. If they're not, it's not so much that we can't perform the tests, or not so much that we have to ignore all the data, but we have to rearrange or adjust our categories. So if I look at this data here, which just X and Y, doesn't actually state what they represent, it's hard to tell right away why this doesn't meet the expected counts condition. You may look right here and go, well, these numbers are less than 5, and so is this. Well, those are less than 5. These are not the expected counts. These are the actual values. So before we can be sure about how we want to adjust things, we need to put all this data into our GDC and find the expected values. And so first, when you do that, you put all this data into your GDC. For example, in the TI-84, you make a matrix that is 4 rows and 5 columns. Put that data in, perform the chi-squared independence test, and you will then see in one of your matrices all these values, but as the same shape of a matrix, but with the expected values, the expected counts. And they're generally fairly messy decimals for all of these. You have to look at those values before you can determine if this has met the expected counts condition. And so once you do that, you'll realize it's actually only this column here that doesn't have values that are all greater than 5, or even if even a single one of these values is not greater than 5, we have to make some adjustment. Whereas if you look at the rest of your expected counts, everything that is in these cells, again, not for the actual data, but for the expected counts, everything is at least 5, if not higher. So in the end, the only problem is this category right here. So how can we still use this data in order to perform a chi-squared test? Well, the simplest way would be to merge these two categories. And instead of having 2 separate categories, just make this one category. That would be X is greater than or equal to 15. If you do that, I feel a little too lazy to copy out the entire table. So if I do that, I can leave everything else the same. But here, I would have, instead of 5 columns, I'd have 4 columns. And the final column would be everything greater than or equal to 15. And I would have 10 here. I'd have 10 here, I'd have 9 here, and have 14 here, just merging those two together. And in doing so, I'd have a table that has 4 columns and 4 rows, which means without even having to perform my goodness of fit test, my chi-squared independence test, I know there's going to be 9 degrees of freedom here, because the degrees of freedom for a chi-squared independence test is always the number of rows minus 1 multiplied by the number of columns minus 1. And again, now once I merge these 2 columns together, I have 4 columns. I always had 4 rows. Subtract 1 from each. I have 3 times 3, so the degrees of freedom is 9. And I could merge more together, but if I merge more together, my degrees of freedom get smaller. And again, we want to keep our degrees of freedom as large as possible. And that's degrees of freedom we'll be talking about more and more in coming lessons as well. So that's it from me for this.